How's it going, everyone? All right. Were there any questions before we get started? Okay. So, today we're going to cover section 9.2 and maybe some of 9.4 also. We'll see how far we can get. And then I anticipate on Thursday we'll finish up the chapter. And then, as I talked about before, next week we'll review on Tuesday and then test on Thursday. Well, since the test will be in a Canvas quiz, it won't actually have to be on Thursday, but I'll give you a window during which you'll be able to complete it. So, what we'll see on the review will largely be like what you see on the exam. So, I think that'll be your best scenario for preparing for the test. So that's what we have to look at. Yeah. Anyway, so we still have all of the rest of chapter 3 to finish first, but let's move forward with that then. So section 3.2 is on measures of dispersion, as you can see here. Now, when we talk about dispersion, the goal here is to discover whether the data is kind of centralized and compact around one general area, or is it more spread out through the data set. So here we're trying to determine if the data is compact, or spread out. Also, we're going to examine what's called the Empirical Rule, and basically how that helps us with what we call normal distributions. Because if the data is not compact or spread out, and then in between there's one we call a normal distribution, and we'll talk about that in a moment. So technically there's a third option here, which means normal. Okay. Now, there's a couple of different statistics we use to help us determine these. We have the range. We'll also look at how to calculate the standard deviation. And that's really it right there. Those are the two primary ones that we consider, the range and the standard deviation. Whenever we look at standard deviation, we also consider variance, but at this point we're not going to do a whole lot with variance, so we will not do too much with that. Okay. If you end up taking like a second statistics class, that's where we tend to see a little bit more stuff with the variance and like analysis of variance. Anyway, so they are going to be directly connected, and I'll mention the variance, but we're not, like I said, not too much time spent on that. So let's examine the range first. Now the range is a pretty easy calculation, and I'll just use R, capital R, to indicate it. But the range is simply the maximum value minus the minimum value. Okay, it's just the difference between the highest data value and the lowest data value. So basically, which data values are we actually looking at in this set, from the lowest to the highest? How far is that distance? Okay, so if we're talking about grades in a class, it's usually a range of, not usually 100, but at most 100. Okay, if we're looking at range of ages in a classroom, that'd be from the youngest to the oldest. We look at the range of shoe sizes in the class, would be from the smallest to the highest, and just subtract, and so on. Anyway, so range is a pretty straightforward calculation. Again, it is subject to outliers. Like if we do have outliers, these tend to be the maximum or the minimum value. I mean, that's by definition what they will be. So an outlier could prove to be problematic here as far as what does the range tell us about the values. And honestly, the range itself doesn't tell us a whole lot about the values. It's really the standard deviation which is going to have a big impact. And the standard deviation ends up being used for a lot of different calculations, as we'll see as we continue through the semester. So it's going to be essential that we're comfortable with the standard deviation as a concept. As far as the calculation goes, it's somewhat difficult of a calculation, but again, we'll be able to use our calculators to do that for us. And I encourage you to let the calculator do that work for us. Okay. So our standard deviation now, you may have noticed last week, I believe I did this. I uploaded a file to Canvas that had a bunch of formulas for Chapter 3 specifically. Also included calculator instructions, so that was part of that as well. Let me do it. First of all, let's do notation before I dive into this too much further. first of all, we have a lowercase sigma, which is a population standard deviation. And we have S, which is the sample standard deviation. Okay. Let's see. I'm not entirely happy with the formula I gave you, because the formula I gave you included frequency, and it's probably best that we don't include frequency. So I'm going to rewrite this formula without the frequency built in. That way it'll be a little bit easier to work with. The formula for S is the square root of n times the sum of the data values x squared minus the sum of the data values of x in parentheses squared divided by n times n minus 1. Excuse me. Now that looks like a pretty rough calculation, and we'll go ahead and do one by hand just to kind of show how that works out. But overall, it again is not something we're going to have to worry about doing, because we'll be able to do that on the calculator just as well. So again, this is the capital sigma versus this being a lowercase sigma. Again, both of those are Greek letters, and inconveniently we use they're both sigma, but there's a big difference between the capital and the lowercase in this instance, which is generally true for most Greek letters. Anyway, so little sigma for standard deviation, population standard deviation, and capital sigma for the summation of the terms that follow. Anyway, and so x is being used as the data value, a specific data value, and we do that for each data value. And then n, if you'll recall, n is the size of the sample. Okay. I'm not sure when you type that, but I'll back up a bit, basically. So we use little sigma to represent the population standard deviation, and we use capital sigma to say we want to add all of these things together. So like for sigma and then x squared, we would say, okay, let's square each of the data values, and then sigma means we add all those values together, all those results together. Whereas here, sigma x means we add all the data values together, and then we square the results. These two expressions here are similar but very different, because the point at which we square the number is at a different part of the order of operations in those two parts. Okay. So that means we'll have to know what our data values are, and then we'll add them all together and square that number. We have to find the square of each data value, then we'll add all those together. And we also have to know what the sample size n is to be able to do our calculation here. Okay. Now, let's go ahead and try that out for a one problem. And we'll start off simple, especially if we're going to do it by hand. So we'll go back to our Fibonacci sequence data. Okay. Now I'll just use 8 terms here, because that'll be relatively easy to work. So we need a column for x. And we also need a column for x squared. Okay. What's our n here? What is n equal to? Eight. Good. Yeah, 1, 2, 3, 4, 5, 6, 7, 8. So let's just list all 8 of those numbers here. That's our first column. Now again, we're going to want to add all those numbers together. And then we also want to square these numbers. So 1 squared is 1. 2 squared is 4. 3 squared, 9. 5 squared is 25. 8 squared is 64. 13 squared is 169. And 21 squared is 441. And so we'll need to add together each of these columns. So for instance, this first column is 2, 4, 7, 12, 8, 20, 33, 54. Then we have 2, 6, 15, 40, 104, 273, and then that was a little harder. Was it 273 and 441? So 7, 14. I'm going to double check that one real quick. Okay. Good. Thank you. All right. So here's our formula again. S equals the square root of n times sum of x squared minus the sum of x values squared over n times n minus 1. Okay. So n we said was 8. The sum of the x squares is 714. The sum of the x's is 54 squared. And then n is 8, so n minus 1 is 7. Okay. So at this point, we just need to calculate what's here. So we take 8 times 714, which is 5712. Then we take 54 squared, which is 2916, and then divide by 56. So we'll do, again, we have to do the subtraction, then we'll do division, and then finally we'll do the square root. 5712 minus 2916. So we subtract that, we get 2796. Then divide that by 56, and then take the square root of that answer. And it gives us a value of 7.066. Let's see. So we might go ahead and just round that to 7.1, because when we talk about, you know, our statistics for whole, if our data is whole numbers like we have here, then we would like to go to 1 decimal place in this instance. Okay. All right. So that's our calculation by hand of the standard deviation. Again, the good news is I'm not going to make you do this. No one should need to do this, ever. Instead, we do have the calculator that will allow us to do this calculation for us. And again, I encourage you to learn how to use it. The bad news is I still have not acquired the AAA batteries I need for my larger graphing calculator, so I will be demonstrating using the smaller TI-36X. Okay, so again here we'll press data, and I'm just going to delete each of our numbers that we have stored here. And I'll enter in each of our numbers: 1, 1, 2, 3, 5, 8, 13, and then our 8th value should be 21, which we see L1 parentheses 8. That means it is the 8th value that we're entering. And it goes on to 9, but this is blank, so we still have 8 values entered. Next, to do the actual calculation, we're going to use this stat button that's on right above data, so we'll go second, and then data, and we want the one variable stats. Our data is scored in list 1, so we want to make sure that's highlighted, and frequency should always be 1. We're not using a frequency column. We'll just enter all the raw data itself, and then we just press enter, get down to calc, and then press enter again. Now we see n is equal to 8, x bar, this is the mean, 6.75, and then Sx, this is our standard deviation, 7.066, basically the same number we got when we did our calculation before. But again, I would stress that we would probably go ahead and round this to 7.1, just because we have whole number data. We want to go to 1 decimal place. Even though it would certainly be more accurate to say 7.066. Alright. Hopefully everyone's okay with that. Let's see. Now again, we could continue down, and we have now you'll notice that this is sigma x. This is the population standard deviation. Notice it's a little bit lower. That's because when we're talking about a population versus a sample, there's different things that we need to consider. Notoriously, sample standard deviation is going to be a little bit larger, just to account for any potential sampling errors that we may have. Like if we have well, it's not really to account for sampling errors, it's just to account for the difference between working with the sample and a population, really. And the idea is that because there's a little bit more uncertainty built into using a sample versus the entire population, we like to err on the side of caution and use a slightly larger number for our standard deviations in those situations. Now, there's actually not a huge difference if we look between. There's less than half of a point, which in this case is not huge. So we're saying if this data represents a sample, we would use Sx, but if we know for a fact that our data is a population, then we'll use the sigma x, which is actually a little bit smaller. And the formula is actually different. Instead of having the n minus 1 down here, I think it's just n squared. And that's really the difference. We have 8 times 8 instead of 8 times 7. Okay. So it's really a small difference in the formulas, but it does have an impact on the values that we get for the two different things. That's why, again, it's always important to know whether we're working with sample or population data. But again, we usually assume that we're working with the sample unless we're specifically told, or we can infer that it is the population. Okay. Because again, working with the sample, this allows us to err on the side of caution for things like the sample standard deviation. Okay. Now, it actually did the calculations for sum of the x's, 54, as we found, and sum of x squared, 714. So if we wanted to go back and double check, and we could actually use those numbers without making this table that we did. It also has the minimum value of 1, median value of 4, and then the maximum value is 21. We'll talk about those a little bit more in section 4 today. So don't worry about that just yet. The Q1 and the Q3 we'll talk about a little bit later. Anyway, so that's how we find the sample standard deviation by hand, but again, that's also how we use the calculator to do it for us, and it's actually a lot easier and faster on the calculator. Okay. Now there will be times where we have to use S in our formula, so those times we'll ask for sigma. Typically, if they ask for sigma in a formula, that means we already know what sigma is, rather than having to calculate it ourselves. If we have to find S, if we have to find the standard deviation, almost certainly we'll be finding the sample standard deviation. Okay. What is the range here, since we're still talking about our measures of dispersion? Good. Remember, our range was our maximum minus the minimum value, which is 21 minus 1, exactly. That's where we get the 20 from. Alright, so we had a standard deviation of 7.1 and R equals 20. Okay. So these are our measures of dispersion for this particular data set. So now the question is the data compact, or is it spread out, or is it approximately normally distributed? And for this, let me bring up my screen here. Let's see. For this, we use the range rule. Okay, and what it does is it compares the range, specifically the range divided by 4, compares that to our standard deviation. Okay, and so if we take the range divided by 4 and compare that to S, if it's about the same, it doesn't have to be exactly equal, it has to be mostly equal, I guess. If it's a little bit off, it's actually okay, we can still call them close enough, and that's a bit of a judgment call at times. So we'll just have to, whenever we do our test, we'll have to make sure we justify our answers. Like if we decide range divided by 4 is approximately equal to S, we feel it's close enough, then we can say, okay, it's a normal bell-shaped distribution based on that. If it turns out that the range divided by 4 is greater than S, then we can say it's compact, like all the data is fairly close together. And if the range divided by 4 is less than S, then we can say the data is pretty spread out. Okay. So, and again, I will actually provide you this whole sheet, actually. This will be provided for the test. So, you don't have to memorize any of this stuff I put on here. This is all like the different formulas that we've talked about. The other stuff here will come from sections 4 and 5. So. Anyway, so our range rule then helps us determine which how do we decide if it's compact or spread out. So in this case, what is our range divided by 4? Good. And we look at our S as 5.1, or sorry, 7.1. Now, we can see this compares, comparing these two, the range divided by 4 is certainly less than the standard deviation. So we can make that statement. What is our interpretation of that then? If the range divided by 4 is less than S, do you remember what we said? Spread out, yes. Range divided by 4 is less than S, so it's spread out. Okay, and that's part of the interpretation that we want to make sure takes place here, because we talked about this. We talked about the shape of the distribution in section on chapter 2. I forget what section. And whether it's skewed left or skewed right or symmetric. And then here we talk about the data, whether it's spread out or if it's compact. Now, actually, let me go back to that document. It's right here. I've talked about, and this is something we didn't discuss in class, is how we can use the median and the mean to determine if the shape of the distribution, basically. Now, going back to what the calculator said, it gave us the mean to be 6.75, and the median it gave us as 4. Okay. So in that case, if we know that the mean is larger than the median, or I guess we should say the median is less than the mean, then what is our conclusion? So we had a mean of 6.75 and a median of 4. If the median is less than the mean, that means the data is skewed right. Because if, again, less than, that's our, remember that's our sign here, that's less than, that's greater than. So yeah, we end up with this scenario where median is less than the mean, so it tells us the data is skewed right. Okay. So that's another part of our interpretation of the data. What does it tell us about the data set? Well, we know the data set's spread out, and we also know it's skewed to the right. So that means there's a pretty good distance between the different data values, we can say on average. And skewed right means that the data is more centralized on the left-hand side, but it has a tail going off to the right. And in fact, because the data is actually not that centralized, it's because we only have 8 data values, then it actually ends up being spread out. Okay, so the center is on the left-hand side and skewed to the right, but then it's spread out across the entire domain, or range, sorry. Okay. Let's do another example. Now, when we talk about the standard deviation, we discussed the formula, but we didn't really talk about what standard deviation actually is. So before we do our next example, let me mention that standard deviation we can call this a measurement of the average distance of each data value from the mean. Now, it's not exactly the average. That's why I said it's a measurement of the average. It's not exactly the average itself, but it's and we see in the formula, but let me show you a slightly different formula. Here we go. This is another way we could calculate the standard deviation. It's not as efficient, that's why I didn't show it to you before. But basically the idea is we take each data value and subtract it from the mean. We square that number, add those together, divide by n minus 1, and then take the square root. So it's not exactly the average, not exactly like a mean of these different distances. That's why I call it a measurement of that. Okay, but it's useful enough because there's other things that it allows us to do that we wouldn't be able to do with a different type of calculation. So when we talk about the definition of the standard deviation, it's basically how far each data value is from the mean. But again, that's not exactly what it's saying, but it's essentially what it's saying. Okay? And so that's why it's useful to compare the standard deviation to the range, although in this case it's the range divided by 4. Because the range divided by 4 is kind of how we expect it to be typically distributed, or where it's like evenly or normally distributed. And then how the standard deviation compares to that tells us how much different our data is from normal. And that goes back to the range rule that I showed you before. Okay. All right. So I wanted to do another problem. Again, this time just using the calculator, I think. And we'll go back to our other data set that we looked at before. So here's our data. So we have 18, 21, 37, 18. And again, this will be closer to what you see on your exam. Something like this where it's 20 to 25 data values. Okay. That's why I think it's imperative that we learn to use the calculators to do this work for us. Just save us so much time. Okay. So there's our data. So again, in our calculator, we're going to press data, and we can either clear out this first list, or I can go to the second list here and enter the data. So I enter 18, 20, 19, 23, 19, and the second row is 21, 18, 25, 20, 29. Now, you see what I just did there? I didn't mean to do that actually, but it didn't hit the 9 hard enough, so it didn't register. So we want to be paying attention to what we're entering. So you can go back up and edit that. In fact, it's worth looking back at all the values. Oops. And then making sure I didn't do that before, because I wasn't paying close enough attention. So 37, 18, 21, 27, 20. And our last line is 18, 32, 45, 19, and 18. Oops. Okay, that looks good. And so we have all 20 values entered into the calculator. So again, press second and data, and we want to go down to 1-VAR stats. Now this time I put the data into list 2, so we want to make sure we arrow over and press enter on list 2, L2. Frequency is 1, and go down to calculate, not calculus, that's my next class. And we see that, okay, we have our sample size, n is 20, x bar, and I'm going to go write down some of this stuff. So x bar is 23.35. S, and actually I should say 23.4. S, if we round to 1 decimal place, is 7.3. Our minimum is 18, and our maximum, we know that's 45 just from looking at that. Okay. And we also need the median, which is 20. Okay. So what's our range? Range is 27. And then what is the range divided by 4? Well, let's see. That would be, it's not quite 7, so 6.75. Okay, now we know in our range rule that we would want to compare the range over 4 to the standard deviation. In this case, would we see these as being, would range over 4 be less than, greater than, or approximately equal to S? Yeah, we should probably say 6.8 there. True. Skewed left. It's still less than, isn't it? Oh, sorry, you're looking over here. My bad. Yeah, if our median is less than the mean, as it is here, and then our R over 4 is less than S, as we see here, then median over being less than the mean, we can go ahead and say that is skewed. This one actually means skewed right. And R over 4 being less than S, I believe that was spread out again. It's okay, unless you have the sheet in front of you, it's hard to remember some of these things. Now, the other question we have to ask ourselves is how close is close enough to consider these to be about equal. Instead of saying spread out, at what point would we say this is normal? Well, what I would say, and this is really a judgment call on our parts, and when we ever go through this, these are about 0.5 apart, which I would say is a little too far to say they're equal to each other. So what I would say in this case, if maybe they were about 0.2 apart, we could start to say they're equal or close enough to being equal. So like if we had 7.3 and we had come up with 7.1, for instance, that might be close enough to say they're equal. Or if we came up with 7.4 or 5, close enough, we might call them equal instead of being greater than or less than. But even if you want to go ahead and say greater than or less than here, and we write the answer that it goes along with that, that's perfectly fine. It's like I said, it's an interpretation. And the same is true here. Now these are far, we can definitely see these are a good distance between them. The mean is 23.4 and the median is 20, so a difference of 3.4 is huge when our range is only 27 to begin with. So we have a relatively small range, so any difference that's that larger percentage of the range, I would say is we can decidedly say that median is less than mean in this case. And I would go ahead and say that R over 4 is less than S in this instance because I feel like these are far enough away. But maybe if there were close to like 0.2 difference between them, something like that, then I would say it's far, unless it's that close, so it's far enough apart to actually make the less than or greater than statement. If we want to be more specific, the rule I like to use personally is 1% of the range, which is 0.27. Anything more than that would be less than or greater than. But I don't want you to have to worry about that too much. And again, that's not a hard rule. That's one that I kind of use myself when I look at these things as far as the judgment call goes. But yeah. And even then, if they're kind of close, we could say, okay, it's spread out, but it's only slightly spread out. Or we could say slightly compact, or they're close, but they're not equal. And that's what we could say in that regard. We can say these are far apart. That's definitely skewed to the right. There's no mistaking that. And there's probably good enough difference between these two that we can say it's spread out, but they're not that far apart, really. It's less than, and like we said, it's about half of a point difference between the two. So, but again, you will have the sheet that has our interpretation of these things. That'll be available to you on the test. I'll make sure I include it. Even better if you have access to a printer and you can print that out. That would be great. But otherwise, I'll include it somehow in the header of the test. So still working that out, but yeah. All right. The other thing that we want to talk about in this section is what we call the empirical rule. And the empirical rule talks about bell-shaped distributions. And so the empirical rule says if a distribution is roughly bell-shaped, and again, that's what we said normal would be. If we have like a normal distribution, it's called bell-shaped. Then that means approximately 68% of the data will lie between one standard deviation of the mean which is to say that approximately 68% of the data will be between mu minus sigma and mu plus sigma. Now again, here we're using mu as the mean and sigma as the standard deviation because we're talking about a population. We could also say x bar and s instead if we're talking about a sample. But usually the empirical rule refers to the population as a whole, although we can apply a lot of its principles to samples if the sample size is large enough. Okay, so 68% is within one standard deviation of the mean. 95% of the data will be within two standard deviations of the mean, which is the mean minus two standard deviations to the mean plus two standard deviations. And then 99.7% of data will be within three standard deviations of the mean. So it's between the mean minus 3 times the standard deviation and the mean plus 3 times the standard deviation. Now, based on this, there's a lot that we'll do basically in the latter part of the course, like starting from chapter 7 on. A lot of what we do in those chapters depends on using this empirical rule. Now, as far as looking at it visually, I can zoom back out there. Looking at this visually, again, our mean is right in the middle. This is what we mean by a bell-shaped curve, by the way. doesn't really look like the shape of a bell, but that's what we call it because we need some way of easily saying it without going through a normal curve distribution or something like that. And then from minus 1 standard deviation to plus 1 standard deviation, between these 2 points, 68% of the data values, I'm going to say actually 34% here, 34% here, in these two individual range, or intervals, or ranges, works. From 2 standard deviations below the mean to 2 standard deviations above the mean, 95% of the data is there. And again, specifically between the first and the second, we can nail that down as 13.5%, as we see here. Likewise up here. And then from 3 standard deviations below to 3 standard deviations above, that should represent 99.7% of the data, which means the only things that we see that are greater than 3 standard deviations in either direction, those tend to be the outliers that we end up talking about at that point. Now what that means is that we can measure a data value's location in the data set using this empirical rule. It does require us knowing that the data is normally distributed, that it has a bell-shaped curve. So we talk about this a lot more in Chapter 7, actually. Okay. So, and even when we get to Chapter 7, although the work's going to be done on our calculators anyway, but, you know, we'll certainly come back to this empirical rule and talk about it more when we get to that point, because that will help us figure out why we're doing what we're doing there specifically. So we kind of introduce it here, but it's not something we'll test on just yet, you know, the topic. So. All right. Turn that light back on. Okay. There's also Chebychev's inequality, and certainly I would encourage you to read about that. But that's getting a little bit more into the more advanced part of statistics, like where does this stuff come from, basically. So it's useful, but it's not essential. So I mean, it gives us some guidelines that we can work with, but again, it's not strictly necessary that we realize where these are in order to be able to do everything that we do. So, all right. Now we'll actually skip section 3.3, so don't worry about that section at all. We're going to go to section 3.4, which is on measures of position and outliers. And I'm going to save this sheet because we'll come back to this and talk about outliers, because we actually want to know definitively what makes an outlier, and are any of these data values outliers. We suspect 45 might be, but we'll see. We'll be able to calculate it precisely. Okay, so when we talk about measures of position, the typical way that we express that is with percentiles or quartiles. You know, if we say and this is used frequently for small children, like when they're growing. You might go to your pediatrician, and they'll get your child's height and weight every time you visit, and they might say, oh, your child's in the 90th percentile for height among other children of the same age and gender, and they're in the 41st percentile for weight. And that means that they're a lot taller than typical children that age, but also slightly lighter than children that age, for instance. And so 50% being the middle, or the median, actually, technically. So a 90 percentile in height means they're a lot above the 50 percentile, above 50, which means they're higher than average. And then if they were in the 41st percentile, that means they're a little bit below average in that sense. Anyway, so that's one way in which we use percentile. Another way is when you are in high school and you're about to graduate, and they tell you your rank in your class. Are you in the top 5%, top 10%, top 25%, whatever, bottom 25%, whatever it is. Then in that case, I mean that's a relative measure of your position among your peers that you're graduating with. And so when you, in Texas at least, I think it's the top 5% or 10%, and maybe it used to be 10 and they dropped it to 5, gain automatic admission to public universities in Texas. I don't know if anyone has any insight on that one, but like if you want to go to University of Texas or Texas Tech or Texas A&M, any of those, if you're in the top 5% of your class, then you automatically gain admission. You still have to pay tuition, of course, but you're likely at that point you're also getting scholarships. So, anyway, so that's another way that we use measures of position. Now, for our purposes, we're not going to dive that deep into it, like with percentiles. Not just yet, at least. Again, we're going to come back to that topic in Chapter 7, which I'm kind of talking up Chapter 7 here, so some of you might be getting kind of leery of that one. But by the time we get to it, hopefully it won't be so bad. But anyway, instead of going through all the percentages, we like to look at, for now, we'll just look at the quartiles, which are kind of like markers as far as different locations in our data set. So our data set might go from the minimum on one side to the maximum on the other side. The minimum is basically the 0th percentile, the maximum is basically the 100th percentile. And we're going to divide that into 4 equal chunks. Right here we have the median, which we could also call Q2, which is the second quartile. Then we have Q1, which is the 25th percentile. So that's the first quartile, which is 25%. And then we have the median, which is the second quarter, which is 50%. And then we have Q3, which is our third quarter, so 75%. So basically, this gives us a way of dividing up our data. Say, okay, 25% of our data values are between the minimum and Q1. 25% of our data values are between Q1 and the median. 25% are between the median and Q3. And the last 25% is between Q3 and the maximum. So basically kind of divide up in chunks where each quarter percent or is for the data set. So it gives us these markers, and then that should help us summarize the data to some degree. Okay, now we already noticed, hopefully, and going back to the calculator, when we got all that data before, notice I said it started with the minimum, which is or 0% or in the left value. Then we have the Q1, 25th percent, median, 50%, Q3, 75th percent, and the maximum, 100%. And so, in that regard, we can say that the percentile or the quartile basically tells us how much data is to the left of that number. So Q1, that means 25% of the data is to the left. Median, 50% is to the left. Q3, 75% of the data is to the left, and the maximum 100% of the data is to the left, including itself in those calculations. Okay. But as far as how we need to find all these numbers, that's already given to us in that same process that allowed us to find, the mean and the standard deviation and everything else that we talked about already. Okay. So it's really the same routine in the calculator that lets us do that. But let's talk about how we would decide on what is an outlier. We have about 5-10 minutes left. So we define our interquartile range which let's go ahead and abbreviate that as IQR. IQR is equal to the difference between Q3 and Q1. So instead of looking at it from max to min being the range, we're going to look at from Q1 to Q3 being the interquartile range. Basically, this kind of designates where the middle 50% of the data is, because we go from 25% to 75%, so that's the middle 50. So that's where we expect half our values will be between those two numbers. That's actually what it means, actually. Half of our data values are between those numbers, another quarter is below Q1, and the other quarter is above Q3. Now, our fences are going to be basically where we mark off kind of the highest and the lowest values that we anticipate getting based on where our interquartile range is, assuming that it's an approximately normal distribution. So for our upper fence, which I'll abbreviate as UF, appropriately enough, this will be Q3 plus 1.5 times the IQR, and our lower fence, appropriately LF, is Q1 minus 1.5 times the IQR. Okay, so the way that we determine if a number is an outlier is any data value that is not between the lower and the upper fence. Okay, so that summarizes our process right there. We calculate the interquartile range, then use that to help us calculate the two fences, and then any of our data values that are not between those two fences are considered outliers. So for our problem, and I'll go back to the calculator for this, we had Q1 is 18.5 and Q3 is 26. So we calculate the interquartile range, Q3 minus Q1, so our IQR is 7.5. Just taking 26 minus 18.5. Okay. Now let's look at our upper fence. For upper fence, we take Q3, which is 26, plus 1.5 times our IQR. Now, we want to be careful with our order of operations here. We actually want to do this multiplication first before we add it to this other number. That's why I like to put that in parentheses, just to indicate, these have to be done first before the other follows. Alright, so, or if you want to, we can do it in parentheses as we enter it into the calculator. Like so. So 26 plus parentheses 1.5 times 7.5. So that gives us an upper fence of 37.25. Now, our lower fence, we start with Q1, which we said was 18.5, minus 1.5 times IQR, or 7.5. And again, let's put that in the calculator. 18 minus parentheses 1.5 times 7.5, and that gives us a value of 6.75. Now, our outlier then is any data value that is not between the lower fence, 6.75, and the upper fence, 37.25. So everything between the two fences is considered a typical value. It's not unusual to get a value in that range according to this data that we've collected. Anything smaller than 6.75 and anything larger than 37.25 would then be considered an outlier. Okay. So we looked at our data set. Do we have any outliers? $45, right? Because did I make a mistake? Yes, it would. Sorry. It actually doesn't affect the outcome, but we want to be accurate, certainly. It's 18.5. I entered 18. So, yeah, that should be 7.25. You're right. Okay, but if we look at our data, the smallest data value is 18 already. It's nowhere near our lower fence, so we're good there. Okay, but we do have some values close to and above the upper fence. You know, we had a 37 value. That was almost an outlier itself, but not quite. 37 is actually between these two numbers, so it was actually okay. It was a little high, but not unusual. But the 45 value is the one that is definitely an outlier. Okay. So again, any number that's lower than the lower fence or higher than the upper fence, those are the values that are considered outliers. Now, we shouldn't expect to get more than 1 or 2 for most data sets, especially at the level of data that we're working at, because a lot of what we do will be 50 data values or less. So in that case, having it would be pretty strange to have more than like 1 or 2 outliers, but not out of the question, but strange. If we're working with like thousands of data values, then we potentially could have quite a few outliers in that case, which would be typical for that kind of data, because it wouldn't necessarily fit the way we'd like it to all the time, and we can't anticipate that. So. All right. Any questions on how we did that calculation? Now, I want to do a little bit more with this next time. So we'll still do another problem on 3.4 here before we move on to 3.5. But that's what we'll be doing next time, and that will be basically the end of chapter 3 at that point. Let's see. Oh, here we go. Oh, sorry. I forgot we looked at 3.2 also. So for homework, let's see. On page 162, I want you to look at (21), part B, C, and D. And then 28A. And then on section 3.2, let's see. Page 142. Look at number 13. Look at 19A. And for 19A, determine if it's compact or spread out. Okay. Sorry about that. Taking a little bit too long there. Hopefully everyone's doing all right though. I'll go ahead and upload the review in case some of you want to get started on it. I mean, next week on Tuesday's class we'll go over the entire review, so don't worry about that too much just yet. Like if you have questions on the review, don't worry about it too much, because we'll definitely go over the whole thing on Tuesday's class. But I want you to make sure you work through it and kind of maybe that'll let you kind of see where you stand right now as far as keeping up with everything versus what you might need to focus on for studying. So, all right, y'all take care. Have a good day, and I will talk to you next time. Bye.